Now we will see what are the properties of angle modulation. Properties. The first one is transmitted power is constant. PAV is equal to AC square by 2R irrespective of KP and KF. Always our transmitted power will be constant. And second, angle modulation is a non-linear process. Our amplitude modulation is a linear process. That when we combine two signals S of t, which is not equal to S1 of t plus S2 of t. That is. And the third one is in terms of noise and spectral analysis. Noise, since it is a nonlinear process, noise and spectral analysis are complex and visualization is difficult due to the factor of irregularity in the zero crossing. And the last one is the trade-off between bandwidth, which we have already seen in the comparison. Trade-off between bandwidth and signal to noise ratio. When you keep on increase the bandwidth, signal to noise ratio will be improving. When you keep on decrease the bandwidth, signal to noise ratio will also degrades. So therefore we have a trade-off between bandwidth and signal to noise ratio. These are all the four important properties of angle modulation. Next we will move on to relationship between PM and FM waves. PM and FM. From the definition we have seen what is FM. FM is theta I, instantaneous phase is proportional to integral over 0 to t m of t and 0 d of t. This is from the time domain expression we can directly write instantaneous phase is directly proportional to integral of our message signal. In the PM, theta I of t is proportional to m of t. Therefore, from this equation we can generalize when if m of t, if we integrate this m of t, that is while passing to an integrator and then to a phase modulator, then our m of t will be integral of m of t dt, then passing through a phase modulator, we will get S Fm of t, that is frequency modulated signal. If we pass m of t to a differentiator, that is d by dt of m of t is passed through the frequency modulator. Instead of phase modulator, here frequency modulator. The output will be, the resultant will be phase modulated signal. Here we will get SFM of t and here we will get SPM of t. This is the relationship between frequency modulation and phase modulation. Next we will move on to frequency deviation and modulation index. How far the frequency, carrier frequency is deviating from the unmodulated carrier frequency. And the most important term is modulation index. Frequency deviation is referred in terms of del f, modulation index is referred in terms of beta. We know that Fi of t, del f is the frequency deviation. It is defined as the maximum departure or deviation, maximum departure of the instantaneous frequency, carrier frequency from the resulting FM signal or the modulated FM signal. Is referred as del f. That is, in terms of equation, del f is equal to Fi of t minus Fc. How much our unmodulated carrier frequency is deviating from the instantaneous frequency of the modulated signal. Maximum. Therefore, we know from the frequency modulation term Fi of t is equal to Fc plus Kf into m of t minus Fc. Fc and Fc will get cancelled out. Therefore, Kf into Am cos 2 pi Fm of t max. We know that cos 2 pi Fm maximum value will be 0 to 1. Therefore, minimum value is 0, maximum value is 1. Therefore, the maximum value for del f is Kf into Am. When you have cos 90 degree, the maximum value will be, for maximum value for cos is 1. When you have a frequency of 0, therefore del f is equal to Kf into Am. Del f is proportional to, from this we can easily understand that if we lay out this proportionality constant term, this del f frequency deviation is proportional to the amplitude of our message signal. It is independent of frequency of the message signal. This is a prime motive, right? Only amplitude of the message signal is containing the information. Therefore, we are varying the frequency of the carrier signal in accordance with the message amplitude of the message signal. And to derive what is modulation index, we will write instantaneous phase. Theta I of t is equal to 2 pi Fct plus 2 pi Kf Am integral over 0 to t cos 2 pi Fmt. These two terms are from the frequency modulation. Therefore, 0 to t cos 2 pi Fm of t into dt. We can rewrite it as 2 pi Kf Am cos 2 pi Fm can be integrated into sin 2 pi Fm divided by 2 pi Fm into t. Therefore, this 2 pi and 2 pi will be cancelled out. Therefore, our final equation will be theta I of t is equal to 2 pi Fct plus Kf into del m can be replaced with del f. Therefore, del f into sin 2 pi Fm divided by del f, sorry, Fm. This term del f by Fm is replaced with a term called beta, that is theta I of t is equal to 2 pi Fct plus beta. This beta is called the modulation index, sin 2 pi Fm of t. This we can take it as equation number 1 and this we can take it as equation number 2. This beta is the modulation index, del f by Fm. Modulation index. So, depending upon the beta value, that is modulation index value, we can characterize our frequency modulation into narrowband frequency modulation and wideband frequency modulation. If we have a beta greater than 1, very greater than 1, then we can characterize it as wideband frequency modulated wave. When we have a modulation index beta with a value less than 1, then it can be characterized narrowband frequency modulated wave. WB stands for wideband and NB stands for narrowband. This is del f is the frequency deviation. This beta is the modulation index. Deviation ratio is given by yet another term. Deviation for non-sinusoidal signals or non-sinusoidal modulations, we usually refer with the value called deviation ratio, which is capital D, which is represented in terms of del f by fm max. These three are very important parameters in frequency modulation. This frequency deviation term, modulation index, and then deviation ratio. We will see what is narrowband modulation, and then how to generate a narrowband modulated wave and how to generate a wideband modulated wave. First, we will see types of modulation based on the modulation index. Types of frequency modulation. Depending upon the value of beta, we characterize it as narrowband frequency modulation, wideband frequency modulation. Now we will derive the expression for time domain expression for narrowband wave. Just now we have seen the instantaneous phase, which is equal to theta I of t 2 pi fct plus beta sine 2 pi fm t. This is the term which we just now derived for the frequency modulation. Beta is the modulation index term. Therefore, S fm of, or we can write NB fm of t is equal to AC cos 2 pi fct plus beta sine 2 pi fm of t. If we take this parameter as A and this parameter as B, then we will get a formula for cos A plus B. Cos of A plus B is equal to cos A cos B minus sin A sin B. Therefore, fm of t is equal to AC. Since this is a constant factor, we can take it as outside. Cos 2 pi fct cos beta sin 2 pi fmt minus sin 2 pi fct sin of beta sin 2 pi fmt. Since we have taken a narrowband modulated wave, for the narrowband modulated wave, our beta will be less than 1. For beta value, since beta is less than 1, cos theta is equal to 1. When you have take a very small value for theta, this value we are taking it as beta. Whenever we have a small value for beta, cos theta is equal to 1, sin theta is equal to theta. This is by trigonometric identity. Therefore, for small values of theta, we can replace cos theta is equal to 1 and we can replace sin theta is equal to theta. By rewriting this equation, AC cos 2 pi fct, this whole term will be replaced as 1 minus sin 2 pi fct, this whole term will be replaced as theta. Therefore, here theta is equal to beta sin 2 pi fmt. So, instead of sin theta, we are going to write it as only this part, theta part, 2 pi fmt. Therefore, S NB fm of t. Now, we are writing it as NB fm of t because we have taken beta value as very less than 1. Therefore, AC cos 2 pi fct minus beta sin 2 pi fct sin 2 pi fmt. Here also we can use a trigonometric identity sin A sin B form. 2 sin A sin B is equal to cos A minus B plus, cos A minus B minus cos A plus B. 2 sin A sin B is equal to cos A minus B minus cos A plus B. By using this formula, we can again write SNB Fm of t. By substituting this formula, AC cos 2 pi FCT minus beta AC by 2 cos of 2 pi FCT minus 2 pi FMT minus of beta AC by 2 cos of 2 pi FCT plus 2 pi FMT. This is a narrow band wave. Here we are having three terms. Again, by rewriting, by taking this minus inside, by rewriting this term, AC cos 2 pi FCT minus beta AC by 2 cos of 2 pi FC plus Fm of t plus beta AC by 2 cos of 2 pi FC minus Fm of t. This term remembers our time domain expression for amplitude modulated wave. If we take this as equation number 1, this is equation number 2 and this is equation number 3. This first term represents the unmodulated carrier wave. The second part represents the upper side band with the change in the magnitude, and this is the lower side band term. Only the LSB part is reversed, upper side band is when compared to the amplitude modulated signal. The phasor diagram part is given by FC minus of Fm is given by, we written anywhere wrong, cos A minus B, therefore minus of FC minus Fm, this is FC plus Fm, therefore okay, here minus, here we are having plus. So this is our LSB part and this is our USB part. So LSB is having the phase reversal. This is our USB part. When comparing it to the amplitude SAM of t, amplitude modulated wave, we are having AC cos 2 pi FCT plus AM AC by 2 or AC mu by 2, AC mu by 2 cos of 2 pi FC minus Fm of t plus mu AC by 2 cos of 2 pi FC plus Fm of t. So only this term is, by comparing these two, only this term is getting reversed. Therefore, by looking into the phasor diagram, so this is the phasor diagram for amplitude modulated wave. This is our carrier AC, this is our LSB, this is our USB, this is the resultant spectrum for LSB and USB. This is the SAM of T, resultant phasor spectrum by addition of the phases. This is our USB, 2 pi Fm of T, this is minus 2 pi Fm, LSB, rotating phases. By vector addition of LSB and USB gives that part. When combining this vector addition with the carrier, the resultant spectrum is the amplitude modulated wave. Now the phasor representation for this is for AM, for FM. So we have a carrier signal and this is our USB. We don't have any change over here. This LSB is reversed here. Therefore, instead of plotting it here, we are going to plot it here. So this is our LSB and this is our USB part. This is a 0, this is our carrier. Therefore, the resultant is, this is our resultants, vector addition of LSB and USB. 2 pi Fm of T, this is our resultant modulated signal for frequency modulation. As Fm of T, the resultant of LSB and USB phasor and the resultant of the vector addition with the carrier. It results in this part. SNB FM is perpendicular to carrier. This. Now we will see the frequency spectrum of narrowband modulated wave. The frequency plot is given by since we don't have any changes in the magnitude part, it will be keep as such. AC by 2, AC beta by 4, AC beta by 4. This is our upper side band, this is our lower side band. 0, this is for narrowband FM. F. In terms of F, this is our FC, FC plus FM. This is FC minus FM. This is minus FC. This is minus FC plus FM. Since we have no changes in the amplitude part, AC by 2, beta, AC by 2, here again beta, AC by 2, minus FC, minus FM. So the frequency plot, by looking into this frequency spectrum, it resembles exactly the amplitude spectrum plot. The only difference we have seen just now, we have seen in the phasor plot. No amplitude variation. Both AM and FM are having the same spectral content.